Hey Class 10, board exams are right around the corner, and I know you need a super fast, super effective way to revise. Well, you've come to the right place. We're about to tackle magnetic effects of electric current and make sure you have every key concept locked down for the exam. Let's do this. So this is the big question, right? How on earth does a simple, boring wire suddenly turn into a magnet? That's the magic we're unpacking today. In the next 5 minutes, we're going to cover everything from those invisible fields to the rules that run the show, and even the safety stuff that keeps us all from getting zapped. Let's get started. You know, the whole thing started completely by accident. Way back in 1820, this guy, Hans Christian Ørsted, was doing a lecture and noticed a compass needle twitch every time he switched on an electric current nearby. That little twitch was huge. It was the first proof that electricity and magnetism were connected. And that discovery, electromagnetism, is the foundation for, well, everything we're about to talk about. Okay, so to really get this connection, we first need a way to see the invisible. We have to be able to visualize these magnetic fields that electricity is creating. So our first stop is all about mapping out these mysterious forces. A magnetic field is just the area around a magnet where its push or pull can be felt. It's like its personal space. And to see it, we draw something called magnetic field lines. Think of them as a map that shows you exactly which way the magnetic force is pointing and how strong it is.
Now this is pure exam gold, so listen up. These field lines have rules. They always flow out of the North Pole and into the South Pole on the outside, forming complete closed loops. And a little detail people forget. Inside the magnet, they go from south to north. But the most important rule of all, they never ever cross. Why not? Well, think about it. A compass can't point in two different directions at the same time, right? Exactly.
Okay, so now that we know how to picture these fields, let's get to the real heart of the chapter, how running electricity through a wire, a conductor, turns it into a magnet. And you'll see how changing the wire shape completely changes the magnetic field. So let's start with the simplest case. You take a straight wire, you pass a current through it, and poof, you get a magnetic field that looks like perfect circles wrapping around the wire. And it's pretty logical. More current means a stronger field, and the farther away you get from the wire, the weaker the field becomes. Simple as that. But wait, which way are those circles going? Clockwise? Counterclockwise? For that, you need a special tool. And this is the first rule you absolutely have to memorize, the right-hand thumb rule. It's a super simple trick to figure out the direction of the magnetic field in seconds. Come on, do it with me right now. Take your right hand. Imagine you're grabbing the wire. Now, point your thumb in the same direction the current is flowing. See how your fingers naturally wrap around the wire? That's it. The direction your fingers are curling is the exact direction of the magnetic field. It's basically a physical cheat code for your exam. So, what if we need a much stronger, more useful magnetic field? We could pump more current through, but there's a better way. We take that same wire and we wrap it into a tight coil, kind of like a spring. This shape is called a solenoid, and it is an amazing way to create a really strong, and this is important, a really uniform magnetic field inside.
And check this out. This is what makes a solenoid so cool. When you run a current through it, it behaves almost exactly like a regular bar magnet. Seriously. It gets a north pole and a south pole, and the magnetic field pattern is practically identical. The big difference? You can turn it on and off with a switch. It's an electromagnet.
Up to now, we've just been creating magnetic fields that just sit there. But what happens if you take a wire that's already carrying a current and you put it inside another magnetic field? This is where things get really fun, because this is where we create motion. This is the secret behind every single electric motor in the world. This is the big idea right here. When the magnetic field from our wire interacts with that external magnetic field, the wire actually gets pushed or pulled. It feels a force. And that, my friends, is how we turn electrical energy into the mechanical energy of movement. Okay, so which way does it move? Up, down, left, right? For that, we need our second essential tool, Fleming's left-hand rule. Now pay attention. If the question asks about the direction of force or motion, you need to use your left hand. Don't mix them up. All right, get your left hand ready. Make an L with your thumb and forefinger, then stick your middle finger straight out, so they're all at 90-degree angles to each other. It's simple. Your forefinger points in the direction of the magnetic field, your middle finger points in the direction of the current, and then your thumb automatically points you in the direction of the force. A good way to remember it is FBI. Force is the thumb, B for the field is the forefinger, and I for current is the middle finger.
Let's bring all this physics back home, like literally into your house. We're going to look at how these ideas work in our home wiring, and more importantly, the safety gadgets that protect us every day. So, in your walls, there are 3 main wires. The live wire, usually red, brings the power in at high potential. The neutral wire, usually black, is what completes the circuit. And then there's the earth wire, the green one. It's the silent hero. It does absolutely nothing until something goes wrong, and then it saves your life. One of the biggest dangers is overloading. This is when your circuit tries to draw way too much current. It could be because the live and neutral wires accidentally touch, that's a short circuit, or maybe you just plugged your TV, microwave, and AC into the same outlet. That overload can cause wires to get super hot and even start a fire. So, how do we stop that from happening? We have 2 main safety devices. First, the electric fuse. It's basically a self-destructing wire. It's designed to be the weakest link, so if the current gets too high, it just melts and breaks the circuit, protecting your expensive appliances. Then there's earthing. That green wire connects the metal body of an appliance to the ground, giving any leaking current a safe path to the earth instead of a dangerous path through you.
Whew, okay. That was a lightning-fast tour. So let's do one last rapid-fire recap of the 3 biggest ideas you need to walk away with. Let's make sure these are cemented in your brain for the exam. First things first, the number 1 rule. If you have an electric current, you have a magnetic field. Period. No exceptions. That's the whole point of what Ørsted discovered.
Second, remember the rules for drawing these fields. The lines are always closed loops, and they can never, ever cross each other. And remember, the closer the lines are, the stronger the field is. And finally, know which tool to use for the job. Your right hand helps you find the direction of the magnetic field. Your left hand helps you find the direction of the force. Don't get them twisted. And I'll leave you with this one last cool thought. The nerves in your body, they work using tiny little electric currents. Which means that right now, as you're sitting here listening, your own brain is generating its own super faint magnetic field. So in a way, you're an electromagnet too. Pretty amazing, huh? Now go crush that exam. Good luck.